Hi everyone, in this video let's see how to build a tiny algorithm, tiny application in PureData PD with the default template we saw already in the previous video. I'm going to show you a tiny application in order to manage all the ports and receptions and sendings of the knobs and all the parts of the physical part of the lich. Here, for example, let's see a concept that illustrates the behavior and the concept of this patch. Well, we have a main kick. This main kick can be trigger in different sections and different positions of between 8 positions. I did in this example, for example. This rate of triggers that we can just trigger one or a couple or even 8, we can control with this amount of triggers knob here in knob A from one trigger only in the left position and full of these 8 positions, therefore 8 triggers in the right position. As you can see here, it's 8x and 1x, because x here it means the incoming, like the rate or the clock of the incoming CV that it's coming outside from other modules. We may be interconnected with Lich. So here we can put the CV from outside, and it's going to calculate internally the milliseconds, the rate, the milliseconds of our algorithm. So with 1x, it means it's just the same speed that we're coming from outside, and on the contrary, 8x, it means it's some kind of expansion or expanded 8 per 8 the rate we are coming here. Another thing that we can control with this main kick is the frequency. It's just you'll see later, but it's very tiny synthesizer, very simple one with one oscillator and one envelope control with the decay, with some section of code that controls the decay. Here in the kick we can control the frequency from low frequencies to high frequencies. That here in this C knob we can control from low frequencies to high frequencies, just on the couple of positions. Another thing to say here in this example is just to these couple of blocks that this corresponds to knob B and knob D, that are like delay times and the delay feedback that maybe you already know, but are like typical couple of parameters pretty interconnected. So delays is like from the main kick, it's the delay time that we can just delay in position the initial trip. Maybe we can just with this knob precisely we can control if we want this delay in one position, in a couple, in 3, and so forth. So here from 0x it means it's just no delay, it's like the same position, and 7x it means it goes from until the last position of the 8, all the 8 possibilities, as well as the same as the amount of triggers I commented before. The gate one is incoming CV clock, so here the delay times are related to that one, so which is pretty cool effect, because you have to, in fact, you are quantizing the delay times in order to make some kind of polyrhythms with just only with one kick in this case, making polyrhythms with the delays because are matching the quantization of time and proportions, which is, we'll see later. It's a pretty cool effect. In addition, of course, as many delays you may know, we have the classic feedback parameter, that in fact is some kind of reinjection or feedbacking, that it goes again if we are playing one delay from the initial one, the more feedback we have, the more secondary and third and fourth and so forth feedback delays are doing, depending on this ratio of feedback. So this is the concept. Let's see now which is the patch of this all of this concept. Here we can see this patch. Maybe it seems pretty huge, but it's not so well. We'll see later why I use in this position, in this composition, like vertical one. We'll see later. Initially, we have here in the top the section that already we saw in the template, that is going to connect gate 1 with button left, and it's going internally to calculate the ratio between a couple of triggers. A couple of triggers here is going to calculate the milliseconds between these two triggers. So it's very useful to set it up like a kind of metronome or clock inside our algorithm. We'll see later how we can use it. Also, we can use the same trigger just to make some trigger, like a message trigger in this one, in this bank. So we can use it for something like maybe we want later in our algorithms. And here we have as well, as I said before, the control of the LED. We have this message to control the LID that we have in the top of the gate out port. Okay, so let's see here how there we have here the control of knobs knob A, B, C, D, which corresponds to all these 4 incoming messages. And here, as you can see, we have different calculus depending on the values that we are going to do. For example, this is going to make some reverse with this tiny piece of code. Is reversing the slider, and here multiplying by 8 positions, because we need for some things that later we'll see these 8 positions. Well, it's making this behavior, controlling with knob A. In other examples, maybe for example this is controlling the frequency of the kick, of the main kick, so it's multiplying by 111 to go from low frequencies to high frequencies, and so forth. It depends on what you're building. You have to adjust and calculate some the calculus in order to work properly your sends here. Okay, here we have the sends, and you will see later all this is very useful to use some kind of, maybe it's like very obvious, but when we are programming in another place, we don't have to move. So it's maybe a good idea to reference what it is exactly. So for example, we know that maybe in another part of the patch that we are using the value of knob A and so forth, all these other messages. So let's start for this first piece of code that corresponds to the oscillator, that the synthesizer oscillator I said before with the red circle here. So the main kick. This is a very tiny synthesizer that actually has the oscillator and the control of envelope here in Decay, with this tiny section with this object line. So here we can income from in the left inlet of oscillator. We can enter in the frequency. So this corresponds exactly to the knob C. So knob C is controlling the frequency between low values, maybe like 20 or something like that, until like 1,000 or sorry, 10,000, very huge frequencies. But anyways, it's just, this is an example to check it out how it works a little bit, to make our basic algorithm in our Lich. We have here therefore the oscillator, the decay time. The decay time it comes from this tree over here. This tree, it's controlling a couple of things. This tree, it's as you can see, it's controlled by button 2 that corresponds to the right button, of course. So anytime we are clicking here in the right button, this behaves like that. It's like changing between 3 different decay times. That here it's going to here in entering and controlling the oscillator, but as well as you can see, it's entering in another line of message, and it's controlling as well decay time ADC that we'll see later. Another part that we have to say here is this part of here of the code that corresponds to the behavior of what I said before, of this amount of triggers if you want to just trick one only kick, or for example in this one there is 4 kicks between 8 possible positions. So here I can simulate here a little bit how it works. The more on the left it's the knob A, the more high value has this H radio button selector. So in other words, it's making some kind of loop. This is a loop, and it's making a loop between 8 steps. This means, in other words, that you have to click and to bang 8 times here in order to extract the bang, the final bang it's gonna be. So on the contrary, if we're going to the top of the right button here in the knob, loop is like 0. So anytime here, anytime it's coming here, the bang, the main bang, it's gonna be triggering our oscillator with the decay time. I remind that this metro bang, it corresponds to the signal we get firstly coming from gate 1 ratio. So it's very useful to just in this case just trick our kick, our oscillator with our decay time. Okay, after see that part, let's see. As I told you before, this is a decay time ADC that we previously saw that we can control with the right button as well. And what is doing that, we'll see here in this right now here, these couple of pieces that on the left it's like ADC1, which in Lich obviously corresponds to in L here in L port. Here there is some tiny attenuator in order to this you can tweak if you want another strength of your ADC of your incoming signal, but here it's like I put an attenuator just to not to be like much more clear, but this is a question of design, so whatever you can try with other values. Here the difference between, well, here it's this ADC1 and here is the ADC2, therefore the in right position. It's pretty similar one of the other, but the difference is like maybe the continuity in time. This is much more continuous in time and even has a decay time shorter than that one, because this is dividing in between 4 and this is dividing between 2. Therefore the decay times are pretty different between, or slightly different between each other. So in order to, you know, it's very useful and maybe nice idea in order to get much expressivity in sound and sound design, to get, for example, some tiny variations. So we know that in this example, for example, the incoming audio signal from in left, its behavior tiny different, slightly different from if we are coming from in R. And this we can apply to many other stuff we have here in the Lich. So this can be a good idea or not, depending on what you're doing, but I like just to well, in this case just to show you, but it's a very you are making some kind of expansion, the possibilities, and making some like to get much plasticity and versatility. Even if you want to connect your outputs in your own inputs, you can connect in between your own lich and making some kind of bending in own bending. Well, anyways, we have these three ones presented. We have this one that it corresponds to the oscillator and the decay, and here we have the couple of lines on incoming signal. So obviously we have these receptions, this sends of message, sends of signal. Remind that the sendings and receives in PD is very important and useful. And here the signal tilde, S tilde, it means that we are sending some cable, signal cable, like some audio cable. Here we have here the receivers, and it's some kind of mix collector here. So after we have collected, here we have the result of this collector that we can throw in one line. For example, here it corresponds to dry signal with no effect at all, that we can put here. I wrote here in a couple of signals. Maybe it's a good idea as well to just divide. This depends on what you are doing and you want to do, but maybe it's an interesting feature to use any output, DAC1 and DAC2, that remind out L, out R, with different signals. So it's some kind of a stereo, asymmetric stereo or something like that. Or anyways, we can have a like a mono duplicated mono signal and coming together in both ports. Here, therefore, we have here the dry signal, and here all this section I'm going to talk about now is the delay section. That let's see which parts have this delay here to build. If you want to build here this one, or tweaking, or making your own delay for other applications. First of all, we need this object, del right tilde, with ID, with a name. This name can be whatever you want. It's just a memory or buffer. So yeah, we need to write this function, the name of the buffer, and this is like the default time in milliseconds. It's like if you don't play anything, it's like by default this is doing this delay of 3 seconds or 3000 milliseconds. But anyways, because we are changing continuously the delay times, this is like it does not work anything. Anyways, so here is the incoming message, the incoming signal from here, from our mix, original mix. Here it comes here, this buffer. So this is the kind of counterpart of this object. This object is like the receiving object for delay, and this object VD tilde is like some kind of the reception and sending to the final mix or to the final line. That you can see is like VD tilde and the same name of the buffer. Like in this case, we have lich delay. In addition, we have this object that controls, that exactly translates some values into this signal process here inside. These values comes from here, that receiving delay time, send delay time is like if it was connected already, but I prefer just to comment here to show you what is going on. And delay time, we saw in here in this image, delay time of the knob B is making some positions according to certain incoming time that already we calculated before here. And it's very useful to make some tiny proportions or respect the main clock. In other words, we can build with just only with delays. We can build just some tiny some kind of polyrhythms and beats that are like delay beats but are related to the first one because are very quantized. So it's a it's a pretty cool effect to do that. You can try it. And well, finally we have just to end the behavior of this couple of objects. We have of course the typical effect that we have mostly in several delay effects. That is the feedback or reinjection. That with this gate we can just extract what is happening in this delayed signal. We can come again depending if this gate is open or not, and going to calculate again. So in case of this are high values, reinjection is high values, this is gonna be like some kind of feedbacking, classic feedbacking effect that you may know. So it's a very cool effect as well. But well, here we are controlling with knob D, with this value knob D that goes from 0 to 1 in this case, just only like so we saw here. Well, in fact, no, it's not from 0 to 1. In Lich, I realized, because in PD you can go from 0 to 0.99, so almost 1 or even 1, but it's gonna make some feedback of your device or your DSP. In Lich, I put this corrector, some kind of threshold. I'm gonna write here the threshold for feedback, because for higher values, the 0.8 it does not work. It does not make the calculus enough clean. So I decided to just put this like some kind of threshold. So anytime we are moving the D knob, this is going to be from 0 to 0.8. So in this case, in our reinjection section here, this is gonna be some kind of feedbacking, of course, but it's not saturating, extremely saturate all the process of this feedbacking inside these two couple of objects. Okay, later, apart from that, here, well, we have some kind of correctors, some high passes. Yeah, you can see here you can manage between this. Maybe it's not just much subjectivity, but well, you can you can finally filter a little bit more if you need, for example, the main kick like in a low frequency, but maybe the delays you want to cut a little bit the frequencies in order to get cleaner the first one. And so maybe we can use these high passes or low passes or whatever if you want to make some lawyering, some kind of to perceive much clean what is the initial signal from the delay signal in this case. Another thing, and finally we arrive here to the bottom, to the end of the page. We have this couple of algorithms that are calculating some randomic values between 0 and 1, because random 100 divided in 100 is making some point between 0 and 1. You may ask, but why didn't use 10 or because maybe with 100 you have much more possibilities of different values, because for example here is 91, so it's gonna be 0.91 instead of 0.9 or something like that. Anyways, this is just tweaking things that you can adjust and try, so which is your favorite one. The difference between this couple of algorithms is just even are exactly the same, except on this section of here of the line, these messages, that the first on the left, the CV out one is gonna do some fast progressions, because here we have 11 milliseconds incoming in the line object. The line, I remind that this is some kind of transition. It makes transitions or fades between a couple of values. So in this case, if it's randomic values and the moves on this slider, it's gonna be like just fast, because 11 milliseconds are very tiny time. And on the contrary, here we have more than 1,000 milliseconds in the line, in the progression, in the gradient. So it's the behavior is gonna be like much more slow, and like some kind of slow motion effect. That is pretty cool, because with only the same algorithm, almost, we have a couple of different data behavior and data extraction, which is a, well, in fact, this is a some kind of generative inspired techniques, which are pretty cool to just build your automated parameters or elements that you want in your patch. Okay, so once presented all these parts of the algorithm, let's check. I have here a debugger that, of course, all the patches I'm showing you in this tutorial are gonna be here in the documentation, in the description. It's gonna be linked to repositories, so you can use it later to check it out and build your algorithms with PD. I remind that PD, I talked with that you have to do. I forget to say that when we are using PD, we have to use PD vanilla. That is in fact the initial version, the most classical initial version one. Developed and programmed firstly by Miller-Puckett. Why we have to use PD Vanilla? Because it's like the more close to DSP. So in other words, it's like the most simplified version of PD that maybe we need to we don't need to have dependencies on libraries or strange abstractions and whatever. So finally, it's a very cool way just to simplify, to make minimal algorithms, not pretty complex, because otherwise maybe your leech will not respond properly. But anyways, let's check with this debugger if all is everything okay. Here I can simulate the clock, the incoming clock. Okay, so it seems it's going all okay in our patch. Before, this is very nice way to test first if our algorithm is interconnected correctly, if it's all messages are doing what we wanted in the concept or in the idea we want to build. So let's go to, this is another section. The another section we'll see soon in the next video, that how to use, once we already have our PD patch, how we can compile and store the patch in the firmware of the Lich. We'll see later in the tutorial. See you later.